In this lecture, we are going to have an introduction to simulation. Simulation is a broad term. It is used in many circumstances. In this class, simulation refers to the methods and applications to mimic the behavior of real systems. So it is not finite element analysis simulation or computational fluid dynamics simulation. We emphasize systems in this course. Through building a model of the real-world systems, we can get a better understanding of them. With a model, we can adjust the parameters and conduct what-if analysis. This allows us to improve the current systems. With simulation, we are not getting exact results of a system. This should be done with analytical solutions such as those you learn from operations research, OR. However, when systems become too complex and unwieldy for OR to analyze, we may resort to simulation as a reasonable alternative. A common strategy with exact solutions is we tend to simplify the problem so that the problem can be solvable with analytical methods such as linear programming, but sometimes it may be oversimplified. With simulation, we can deal with the exact situations of real-world systems, although most of the time we also need to simplify the model. However, since it is simulation, the answer may not be exactly the same as the analytical solutions. With a simulation model, we can play with it to see the responses due to different parameter settings. In this course, we focus on discrete event simulation. We do also include continuous modeling briefly. Many of the real-world systems are discrete event systems. Manufacturing can be discrete or continuous, depending on the product we are trying to make. If we are making, for example, hammers, they are countable products. They belong to discrete manufacturing. In petrochemical plants, we deal with oil and gas. They belong to continuous manufacturing because the product is not countable as items. Distribution, transportation, and healthcare system are just a few other examples of discrete event systems. We have talked about systems a lot so far. The system in this course refers to a set of physical facilities or processes linked together through some communication methods. We can build a model for the system to study its performance and improve it if possible. Our model looks like a flowchart with parameters. Model is an abstraction of the real system. To make the model match the real system, we need to test the model validity. A model can be physical or logical. A physical model uses physical objects or symbols to build a simulation. In this class, we build mathematical models with arena simulation software. For a simple model, we can use traditional mathematics to get analytical solutions. With more complex systems, we need simulation to help analyze them. Simulation can be done with paper and a pen. We actually are going to go through a manual process in Chapter 2 before we use software to handle more complex simulation. Going through a simulation model manually helps us develop insights into simulation as an analysis tool. For complex simulation, computer simulation is the only feasible way currently. Computer simulation is a popular tool in both academia and industry. Simulation allows us to improve the system no matter how complicated they are. It is able to accommodate uncertainty, nonlinearity, and stochastic problems, which are hard to handle with traditional mathematical methods. Simulation is made possible for large complex systems by the advance of computers. The bad news for simulation is that we usually get only approximated results. Also, the input data to the model is extremely important. If the input date is garbage, we are going to collect garbage as output. RIRO means random input and random output. Therefore, it is important to carefully analyze input date before they are used for simulation. We can categorize simulation in many ways. First, if the parameters change over time, the model is a dynamic model. Parameters may change continuously or only at discrete points over time. Rockwell Arena can handle continuous discrete or mixed continuous discrete model. Models that have no random input are deterministic. Stochastic models operate with at least some inputs being random. For example, a bank may have randomly arriving customers with varying service times. Most operational models are dynamic, discrete change, and stochastic. It is tedious to simulate anything manually. Nowadays, we all use computer simulation. What methods can we use to run simulation with computer? We can use general programming languages such as C++ or Java. In the past, people have developed packages to support common functions needed in simulation. We can also use spreadsheet programs such as Microsoft Excel to run a simple simulation. Researchers have developed special language designed for simulation. Rockwell Arena is built on Simon language. Arena is high-level simulator with graphical interface. Within Arena, we can still use Simon to build a simulation. We can also take advanced model components returned in general-purpose languages such as Visual Basic or C++. This figure clearly describes the structure of Rockwell Arena. It has 6 levels of modeling. The lowest and the most flexible one is to use Visual Basic or C++. On top of that, it is Simon language. The higher levels are with graphical interface. We will spend much time on basic process, advanced process, and advanced transfer panels. This is another way to see how Rockwell Arena is built. The core is the Simon language. Arena is software on Windows platform. It conforms to ActiveX automation standard. With this standard, it can exchange information with many other Windows software that also conform to ActiveX standard. These include Microsoft Office, AutoCAD, and MATLAB to some extent. Nowadays, simulation is widely used and affordable. If you work as an industrial engineer one day, you will very likely ask to build a model for computer simulation.